So welcome you to today's lecture. So let me first ask if any one of you have any doubts from the last lecture or any of the previous lectures. You may ask your doubts now. So any doubts from anybody? So if there are no doubts, let me move forward. So let me do a brief recap of what I did last time. So last time we did a result, so last time we introduced the notion of randomized estimator. So what you do in randomized estimator is, after you have observed X, you observe another random experiment which depends on X. And you take the observed value of this observed random variable as the value of the estimator. Unlike in the non-randomized estimator case, where after observing X, you directly calculate the estimator and no further randomization is necessary. Then I did a result which says that T be a sufficient statistic and let delta be X in estimator. Now this could be a randomized estimator of estimate psi theta. Then I can always find an estimator delta star T, which itself could be randomized, based on sufficient statistic T, whose risk function will always be same as the risk function of the original estimator delta. So what it suggests is, given any randomized estimator delta, I can find another estimator, which is possibly randomized, whose risk is same as that of the given estimator. Or in other words, it is enough to consider estimators based on sufficient statistic. That is what it says. Given any randomized estimator delta, I can find an estimator delta star, which depends on the sufficient statistic, such that the risk of delta star would be same as risk of delta. In other words, what it conveys is, given any randomized estimator, I can find a randomized estimator based on the sufficient statistic, whose risk is same as that of a given estimator. So it suffices to consider only estimators which depend on sufficient statistics. Then we introduce the concept of a convex function. I said a function phi, which is defined on an interval in real line, is said to be convex or concave if phi of alpha x plus 1 minus alpha y is less than or equal to for convex and greater than or equal to alpha times phi x plus 1 minus alpha times phi y, which is equivalent to saying that in the case of convex, the chord joining any 2 points on the curve is always above the curve for the convex. And for concave, the chord joining any 2 points on the curve would always be below the curve. Other way to look at it is, if I look at any tangent on the curve, the tangent would always be below the curve in the case of a convex function. And if I look at any tangent over here in the case of a concave function, the tangent at any point on the curve would always be above the curve in case of a concave function. And then we did some properties of a concave and convex function. Now let's do one of these famous inequalities which we do in statistics, which is called the Jensen's inequality. It says if phi is a convex function defined on an open interval I, and x is a random variable with probability that x belongs to I as 1, and finite expectation. So phi is convex on an interval, x has a support on this interval, then expected value of phi x would be greater than or equal to phi times expected value of x. And in case of concave, it would be less than or equal to, because if phi is convex minus phi is concave minus phi is convex, So you can take minus phi and apply this inequality. We'll get other ways in terms of phi to be less than equal. Now, if phi is strictly convex, the inequality is strict unless your random variable is degenerate. So for strict convex functions, you'll get a strict inequality unless your random variable is degenerate. Now, the proof is very simple. You know that since phi is convex, so for every x naught in I, there would exist a m, which is basically a slope, depending on the point you have chosen, such that the phi x would always be, in the case of convex, what happens is the curve is always above the tangent. So this would always be greater than or equal to the tangent joining x naught and phi x naught would be phi x naught plus m times x minus x naught, where m is the slope of the tangent at the point x naught. So for every x naught in the interval, I can always find a m which depends on x naught, says that this happens. So I can, yeah? Any doubt? Does anyone has any doubt? Okay. So what I do is I can take x naught to be mu, which is expected value of x. And then I apply this to random variable x. So phi x would always be greater than or equal to phi of mu plus m, which only depends on x naught, which is mu, then x minus mu. So then there exists a m. Of course, m only depends on mu. It is not a random quantity. I take the expected value on both the sides. It gives me expected value of phi x. Because you know that if random variable x is greater than or equal to random variable y, then expected value of x is always greater than or equal to expected value of y. So this expected value of phi x would be greater than or equal to phi mu plus m times x minus mu. Phi mu is a constant. So phi mu plus m is a constant, and then expected value of x minus mu is 0 because I have taken mu to be expected value of x. And this is same as phi of mu is nothing but expected value of x. So this is what you get. Now, the example of convex functions are many. Phi 1x is equal to x squared. So if you apply it to this, you get expected value of x squared would always be greater than or equal to expected value of x whole square. Okay? If you apply to phi 1x equal to x squared. If you apply phi x to mod x, x squared is a convex function. Why? Because its double derivative is 2, which is always positive. Mod x is always a convex function because it is like this. If I join any 2 points, the chord is always above the curve. So when I apply Jensen's inequality to mod of x, I get expected value of phi of x, which is mod x, would be greater than or equal to phi of expected value of x. So that means mod of phi is mod, expected value of x is. So that is this inequality. In fact, mod of x to power p is a convex function. So expected value of mod of x to power p would be greater than or equal to mod of expected value of x to power p for every p greater than e to power x is a convex function because its double derivative is e to power x, which is positive. So if you apply Jensen's inequality to this, you get expected value of e to power x is always greater than or equal to e times expected value of x. Log of x is a concave function because its double derivative is minus 1 upon x squared. So if I consider minus log x, it is convex because double derivative would be positive. So if I apply to that, I get expected value of minus log x would be greater than or equal to minus log of expected value of x, or expected value of log of x would be less than or equal to log of expected value of x, provided the expectations exist. Similarly, expected value of 1 by x is a concave function. 1 by x is a convex function because its double derivative is positive. So you get expected value of 1 by x is greater than or equal to 1 times expected value of x. So you see, we have got these many inequalities just using the Jensen's inequality very easily. So these are some of the examples of concave functions. So these inequalities I have plotted over here. Expected value of e to the power x is greater than e to the power x. These all are strict convex functions. So unless x is degenerate, these inequalities would be strict. So this is this. Now note that it is reasonable to assume that any loss function L theta d is convex in D. Why? Because you want your loss to be such that as you move away D, as D moves away from the true estimate tau theta, the loss would increase because the distance between tau theta would increase. So that means, and its minimum should be at D is equal to tau theta. So if it is tau theta, I get a minimum. And as I move away from tau theta, D should increase. And that is what is happening over here. So such a function looks like a convex function. Not always all the convex functions may be of this type, increasing and decreasing. You may have a convex function which is increasing also, like this. But in general, I may assume that my loss function would be convex. So all functions of this type would always be convex. They are bowl-shaped functions. All such functions would be convex. So it looks like it's reasonable to have your loss functions to be convex. So I have shown that mod of x is convex, so I can take L theta d to be mod of d minus psi theta. This is called absolute error loss function. Another convex function is phi x equal to x square. So if I consider that, then L theta d I get as d minus psi theta whole square, which I call as an squared error loss function. Now note that these two loss functions are symmetric. That means mod of d minus psi theta is same as mod of psi theta minus d. That means overestimation is by amount c is as serious as underestimation by c. Right? So if you estimate psi theta d by psi theta plus c, so overestimating, you get error as c. If you're underestimating by psi theta minus c, still you are getting mod of c as the error in both the loss functions. So overestimation by the same amount is same as the underestimation by the same amount. So, and that is why these loss functions are symmetric. But sometimes you may have situation where one kind of overestimation is considered more serious than the underestimation. So for example, if you have to estimate the demand for something for which you have to spend money, if you have overestimated, then you may incur a lot of extra expenditure, and that may be more serious than falling short of some material, falling short of demand. And it may happen vice versa. Sometimes underestimation may be more serious than overestimation. So this demands that we should have our loss functions which are non-symmetric also. So one such non-symmetric loss function is of the type L theta d, which is e to the power a d minus psi theta minus a d minus psi theta minus 1. It's a linear exponential loss function, and it is called line x loss function. Linear exponential line x loss function. Now note that e to the power x is always greater than or equal to 1 plus x. So this quantity is always positive. This is a convex function. Psi x is equal to e to power x minus 1 minus x is a convex function because double derivative would be e to power x, which is always positive. This LP norm, L theta d is mod d minus psi theta to power p. This is also a convex function. For p greater than 1, at least it is convex function. So this is another loss function. So sometimes I may be my psi theta estimate may be the vector value, psi 1 theta, psi 2 theta, and psi k theta. And your loss function may be other types, summation I is equal to 1 to k, mod of d minus I theta to power p, where p is greater than 1. Because for p greater than 1, these are convex functions. Now let me do this result. So the discussion so far suggests that I should consider loss functions which are convex. Now let us look at if the situation is that loss function is convex, then the next theorem says that it is enough to consider only the non-randomized estimators. You don't have to go for a randomized estimators. So let us do this theorem. Suppose that the loss function L theta d is a convex function of d for every theta belonging to R or Rk. Let delta be a randomized estimator. So delta is a given randomized estimator of the estimate psi theta. Then there exists a non-randomized estimator delta star of psi theta, whose risk is smaller than that of the given randomized estimator. With the strict inequality above, the loss function is strictly convex. So very useful result. What it says is that if a loss function is convex, then there is no need to consider randomized estimators. It is enough to consider non-randomized estimators because given any randomized estimator delta, you can find a non-randomized estimator delta star whose risk is always smaller than the risk of a given randomized estimator. So the idea is very simple. What is being done in the randomized estimator is you have a random variable yx for a given x. So what it says is rather than looking at yx, just look at the expected value of yx. So for example, if yx, if your randomized estimator, so let's say x is normal theta 1, and your randomized estimator is yx, which is normal x1, what it says is after you have observed x, don't take the decision right away. You observe one random number from normal x1 and take observed value of that as your estimator. So what is being done over here is it says to remove this randomization rather than considering this random variable yx, I can consider its mean so that it is a fixed quantity. So it says you consider expected value of yx, which is only x. It is only depends on x. And that is no randomization over here. So this is a non-randomized estimator. So I can define delta star x to be expected value of x for every x point. Since this only depends on x because expectation has been taken, so your randomization has vanished. So delta star x is a non-randomized estimator. Now I consider the risk, the first stage risk of m theta delta x, which is the average risk over randomization yx, so which is expected value of L theta yx. This randomization is over that randomized estimator. But I know that this function is convex in yx. So by Jensen's inequality, this would always be greater than or equal to L theta expected value of yx because it is convex in y for every fixed theta. But L theta yx is same as L theta delta star x. So what you get as R theta delta? R theta delta is expected value of this quantity, which is equal to m theta delta x, would always be greater than or equal to expected value of L theta delta star x. But for randomized estimator, there is no first stage of randomization, so this is same as the risk of delta star, so it is R theta delta star. And you know that if your loss function was strictly convex and x was non-degenerate, there would be a strict inequality over here. So I have this remark which says that in an estimation problem with convex loss function, given any randomized estimator delta x, there exists a non-randomized estimator delta star x that is as good as the randomized estimator delta x. Or in other words, whose risk is always smaller than the risk of given randomized estimator delta x. Or in other words, it is enough to restrict attention to only non-randomized estimators if your loss function L theta D is convex in D for every fixed theta. So now I do this famous Rao-Blackwell theorem, which basically conveys that the last theorem says if your loss function is convex in D, then you can consider only non-randomized estimator. This says even among non-randomized estimator, if your loss function is convex, you can consider only those non-randomized estimator which depend on observations only through sufficient statistics. So let T be a sufficient statistic for P is equal to F theta, theta belonging to theta, where theta is a subset of RK. For estimating psi theta, suppose the loss function L theta D is strictly convex in D for every theta belonging to theta. Then given any non-randomized estimator delta star x of psi theta, there exists a non-randomized estimator eta T based on the sufficient statistic T such that our risk of eta, which depends on T, is always smaller than the risk of delta star. With a strict inequality above, if the loss function is strictly convex. So that means given any randomized estimator, given any non-randomized estimator, I can find a randomized estimator which is a function of a sufficient statistic and whose risk is smaller than the risk of the given estimator. So idea is simple here. Delta star x was given. So what I do is I take expected value of delta star x given T. Now note that T is sufficient. So conditional distribution of x given T does not depend on theta. So this expected value does not depend on theta. Because T is sufficient. Since T is sufficient, and because of which the conditional distribution of x given T does not depend on theta, so this expected value will not depend on theta. Because note that if this quantity was depending on theta, I cannot take eta T to be an estimator. Your estimator cannot depend on unknown parameter. So it was important that this expectation does not depend on theta. And that is ensured through the fact that T is sufficient. So clearly, eta is non-randomized because it is just expected value of x. It will only depend on T of x. Let us consider the risk of delta star. Risk of delta star is same as risk of expected value of L theta of delta star x, which is same as expected value of, what is this quantity? I can write down this as expectation of a conditional expectation. Now I applied a Jensen's inequality in the inside expectation. My loss function is convex in D. So expected value of L theta delta star x given T would be greater than or equal to L theta expected value of delta star x given T, which is nothing but L theta, and this quantity is eta T. So this expectation is always bigger than or equal to L theta eta T. So expected value of this quantity would be bigger than or equal to expected value of L theta eta T, which is nothing but R theta delta star would be greater than or equal to expected value of L theta eta T. But this is nothing but the risk of eta. So in an estimation problem, suppose that the loss function is strictly convex, then given any estimator, possibly randomized, there exists a non-randomized estimator delta star T based on sufficient statistic such that r theta delta star would be less than or equal to r theta delta. Which is very simple, because if your loss function is convex, then first of all, given any loss function and given any estimated delta, I can find an estimator which depends on a sufficient statistic. The loss function is convex, then I can find, given any estimator, I can find given any randomized estimator, I can find a non-randomized estimator, provided loss function is convex. Then given any non-randomized estimator, I can find a non-randomized estimator based on a sufficient statistic, which is better than any given estimator. So this says, everything summarizes to the fact that it is enough to consider only non-randomized estimators based on sufficient statistic, provided your loss function is convex in D. So that was about Rao-Blackwell theorem. That was a brief discussion about the elements of the parametric point estimation. Now we'll go to the next topic, which is about the unbiased estimation. But before I do that, let me ask if any one of you have any doubt on the topics which I covered today. Then I can move to the next topic. Okay, if there are no doubts, let me move to the next topic, which is about unbiased estimation. Let me share those slides with me. Any questions from whatever I covered today? Okay, let me just open the next. So what I can do is, let me see if I can pick up few exercises. Okay, let me just pick up few exercises so that I can give a feel of okay, so let me just do this example. Sorry, needed a whiteboard, right? Whiteboard, so, okay. So let us do this example. So suppose Suppose I have a random sample, x1, x2, xn, IID, normal, theta 1. Theta belongs to theta, which is R. I'm saying my estimator, let us say, is consider a non-randomized, or consider a randomized estimator. Delta star or delta x, which let us say has a distribution which is normal, and I can consider this as median of x1, x2, xn. And the loss function is d minus theta whole square or theta minus d whole square. So the first question is find randomized estimator based on sufficient statistic that has the same risk as delta x. Then, because loss function is convex, so you can find an estimator which is better than delta x. Find a non-randomized estimator that is better than delta x. What it means is whose risk is always smaller than delta x. So these are the two problems, suppose you have to do. How would you do that? So let us see what result I'm trying to use. The first result which I'm trying to use is about, let me just mention that result so that this is the result which I did yesterday. It says that given any randomized estimator, delta, I can find a randomized estimator based on sufficient statistic whose risk is same as that of a given estimator. And how did you obtain that? You just look at the conditional distribution of x given t, and you took the average of pxa over that one. So in this case, what would be your t is equal to x bar is sufficient. Note that if you have to consider sufficient, the natural question comes is which sufficient statistic to use. Because given any estimator, you can find a function of a sufficient statistic, t. So you would find, you choose that sufficient statistic which is a function of every other sufficient statistic. Because if that is not happening, you can further improve upon that estimate, because you can choose then the minimal sufficient statistic that would be a function of any other sufficient statistic. So it looks like among sufficient statistic, I should always choose T to be minimal sufficient. So in fact, it is minimal sufficient. Because if it was not minimal sufficient, because if it was only x1, x2, xn, I can always choose estimator based on x1, x2, xn conditioned on T, which is x bar. That would be better than the one which is based on x1, x2, xn, although both were sufficient. So T is x bar sufficient. So what is the P? So first of all, what is your PXA? It is normal with this as median, right? So this is same as 1 by root 2 pi e to power minus 1 by 2 a minus x median, let's say, whole square, where xm is median of x1, x2, xn. So what is your PTA? It says you take expected value of PXA with respect to conditional distribution of x given t, x given t. Which basically is same as saying that you look at P of, so here what is happening is you're integrating of x, so that is same as P of expected value of whatever you're putting over here. You take that with respect to expected value of x given t is equal to t, where P is given by this. So I need to find out what is P of expected value of x given t. That would be the better estimator. So what is expected value of x given x bar? P of t, no, you have to take the expectation with respect to x given t. Yeah, so PXA basically is nothing but, let me write it down so that you understand this. This is same as phi of a minus xm phi of a minus xm f of x given t, x given t. So what does that mean? This is nothing but, yeah, expected value of phi of a minus whatever this is, median of x1, x2, xn, given that t is equal to t. That means given x bar is equal to t, which is same as expected value of phi of a minus median of x1, x2, xn minus x bar. X bar is same as t, so I can add this, given that x bar is equal to t. But what is median of x1, x2, xn minus x bar? That is ancillary. And x bar is complete sufficient, so they would be independent. So this conditional expectation would be same as expected value of phi of a minus median of x1, x2, xn. At least it should be this median of x bar, this median of minus x bar. So you have to find out this expectation, which may be complicated because it will involve the distribution of median of x1, x2, xn minus x bar, which is ancillary. So this is the rule which is better than this quantity. Now I can find an estimator which is better than this by just considering. So if this yx is this estimator, I just look at expected value of yx. So if I have to find a non-randomized estimator better than this estimator, I have to just look at the mean of this distribution. What will be the mean of this distribution? So if my density is this, I have to find a mean of this. So that would be the estimator better than this. Slightly complicated example because you cannot calculate very precisely or in a closed form the distribution of median of x1, x2, xn minus x bar. That certainly will not depend on theta, but it conveys the idea how you have to construct the estimator. Let us look at a simple example. Let us say x1, x2, xn, same thing. IID, normal, theta 1, same example. Delta is a randomized estimator. Y, which has same distribution as normal with mean x bar and 1. Now, if I have to find an estimator which has an estimator based on a sufficient statistic which has the same distribution as this, so what I have to find is, so this certainly is based on a sufficient statistic, so I don't have to bother about it. But yeah, suppose I have to find this was normal x11. Okay? Randomized estimator was normal x11. I have to find an estimator based on a sufficient statistics x bar, right? X bar. So let us say PT, then A would be the density of this, which is phi of A minus x1. You have to take the integral over this with respect to the distribution of x given t, x given t, and dx. But here x is coming over here, so this is same as phi of A minus expected value of x1 given t, which is same as phi of A minus, what is the expected value of x1 given t? We have calculated last time, you can use the Basso's theorem. It would be expected of x1 minus x bar plus t, so this would be t, which is x bar, so phi of A minus x bar. So note that what it says is if your delta was non-randomized estimator, which says that after observing x, we just generate one observation from normal x11. It says you can improve upon that by choosing a randomized estimator, which says that after the data has been observed, you generate one observation from normal x bar 1. That would be having the same risk as this estimator. They both have the same risk. That is what it says. Now suppose I have to find an estimator, a randomized estimator better than delta is. Now delta has same risk as this, and a non-randomized estimator, which is better than this would be, I take the mean of this, which is just x bar. That is what the second theorem says. So this illustrates some applications of your last example. I can now go to the next topic, which is about the unbiased estimation. Yeah, this is done. Let me. Yeah, so this is the module 4, which is about the unbiased estimation. Note that the risk function is given by expected value of L theta delta X. So as I have said, now from onwards, we can forget about our randomized estimators because normally our loss function would be convex. And I know that if loss function is convex, I can only restrict to the non-randomized estimators. So the risk function R theta delta is expected value of L theta delta X. This measures the preciseness with which delta estimates the estimate psi theta. Now, one would like to choose delta that minimizes the risk for every theta belonging to theta because theta you do not know. So this risk is going to depend on theta. And the estimator would be best if it has a minimum risk for every possible theta. But unfortunately, that cannot be done, or you cannot find an estimator which minimizes the risk for every theta, as is clear from the following example. For fixed theta naught belonging to theta, so I fix theta naught. Let us say in the normal theta 1 case, I fix 1, mean as 1. Consider the estimator which only estimates always this by a constant. Very lousy estimator. It says I'll not use the data, I'll always estimate the estimate by the fixed quantity, which is psi theta naught, where theta naught is fixed. Now, if I consider the risk of this, because in this case, delta naught X is a degenerate random variable, it would be expected value of L theta naught delta naught X, but delta naught X is degenerate as psi theta naught, so it would be just L theta naught psi theta naught. But I know the loss at psi theta naught, the value is 0, so this would be 0. So this estimator has the smallest possible risk at theta naught, psi theta naught, which is a constant estimator and does not use the data at all. This is a highly undesirable estimator because it doesn't use the information contained in the data. But it can minimize the risk only at one point to the minimum possible, which is 0, only at one point. So you can always find estimators which minimize the risk at a single point. No other estimator can have a risk 0 at that point, other than that constant estimator. So this suggests that it is not possible to find an estimator that minimizes the risk at every possible theta. That is because of the presence of these kind of notorious estimators. They're notorious in the sense that nobody would use them because they are constant. They don't use the data at all. So for example, in the normal theta 1 case, somebody says, irrespective of what you observe, I'll estimate mean by 1. Such an estimator minimizes the risk at theta is equal to 1 to the minimum possible, which is 0. Thus at parametric point theta naught, delta naught has the smallest possible risk 0, and no other estimator can have a smaller risk than delta naught at parameter point theta naught. That there exists no uniformly best estimator. That is, no estimator exists which minimizes the risk for all values of theta, except in the trivial case where your estimate itself is constant. That means it is not a parameter, it is constant. Now, one way to avoid, so one has to understand why this was happening. This was happening because these kind of notorious estimators, which are totally useless, but they create nuisance in the sense they can minimize the risk only at one point. So the idea is you just get rid of such estimators by imposing certain reasonable criteria. So one way to avoid this difficulty is to restrict the class of estimators by ruling out estimators which do not possess certain desirable characteristics. So I don't consider a class of all estimators because they have highly undesirable estimators like the constant estimators, which I don't want. So I want to pose certain reasonable restriction to restrict my class of estimators. One such desirable characteristic is unbiasedness. What does unbiasedness says? That if I use the same rule a large number of times, on an average, I should get the value of the estimate psi theta. Or in other words, an estimator delta x is said to be an unbiased estimator of psi theta if expected value of delta x is psi theta for every theta belonging to theta. What does it mean? That means because estimator is a rule, if I have to use this rule a large number of times, on an average, the value which I'll get would be the same as the estimate, which is a very reasonable condition. Certainly, any constant estimator will not satisfy this, because any constant estimator, if you use large number of times, it would be the same constant, and it cannot be same as psi theta. So this looks like a reasonable condition to impose to restrict the class of estimators under consideration. Now, if there exists an unbiased estimator of psi, the estimand will be called U estimable. So any unbiased estimator will be called, any estimand will be called U estimable, provided an unbiased estimator for such an estimand exists. So let me stop today over here. We can start from here on Monday. Now, if any one of you have any doubts, you may stay back for discussion. Others may leave. Okay, if there are no questions, if anybody has any questions, may stay back. Others may leave.
Sir, can you please explain the basic definition of loss and risk function?
So,
in simple way, sir.
Yeah. So let me. So let's look at what are the things you have in any estimation problem. You have a sample, x, which is x1, x2, xn. This has some joint distribution, let us say, of theta. Theta belongs to some parameter space theta. Tau theta is the estimate. The quantity you want to estimate based on this sample x. Delta x, let me call, if I'm considering only the non-randomized estimator, delta x is an estimator. Now note that tau theta is unknown to us. I'm estimating this by a random quantity delta x. So there are certain consequences when you estimate tau theta by delta x. And I denote that by a loss. So loss in estimating delta x, sorry, in estimating tau theta by delta x, right? Because delta x is just an approximation of tau theta, because it is an estimator. It is not exactly same as tau theta. In fact, tau theta, you do not know what it is. I can denote this by L theta delta x, right? Because it depends on theta, because theta is varying over capital theta, and you're estimating it by delta x. So this is L theta x. So what is this? This quantity is loss in estimating the estimate which I have, which is tau theta by delta x. Now, this is a function of what? It is a function of theta and a delta. So it's a function of two variables, parameter as well as, but this is a random quantity. You see, my goal is to find a delta for which this is small. This quantity is small. But what I observe is that this quantity is random. This will keep on varying each time you take a sample. So it makes sense about what would be my average loss, which I call as a risk. So R theta delta, which I look at, I take expected value over all possible values of X from the distribution. Now this is the average risk, average loss, average taken over all configurations of the sample, or risk function. And what is the risk function? This is the average loss in estimating my estimate tau theta by delta. So that is the risk function. So the idea is to find an estimated delta for which R theta delta is minimum for every theta, because theta doesn't know, you don't know. So R theta delta is a function of a theta, which you do not know, which is unknown to. So you would like to find estimated delta for which this risk is minimum for every theta, whatever true state of nature may be. But we have seen that it is not possible to minimize this risk for every theta, because you can always choose a constant estimator like delta x equal to theta naught or tau theta naught. If you consider the expected risk of that, that would be expected value of L theta delta x, but delta x is degenerated tau theta naught, so that would be L theta tau theta naught. At theta is equal to theta naught, the risk is become 0. So it is not possible to minimize this at every point theta. So then what we do is we put certain reasonable restriction in the class of estimators under consideration, so that all these undesirable estimators like constant estimators go beyond our consideration. And then within the class of these restricted estimators, I try to find the best estimator. That is a possibility. And one such reasonable restriction is the unbiasedness. Any other question? Is that clear? Does that make sense what I talked about? Or?
Yes, sir. Yes, sir.
Okay.
Clear. It is clear.
Okay.
Thank you, sir.
Okay. Any other doubt anybody has?
No, sir. Everyone left.
Okay.